Hello everyone. My name is Yuan Tongzhang and today I'm excited to present our paper accepted to CVPA 2025 titled Continuous Space-Time Video Resampling with Invertible Motion Steganography, co-authored with Professor Zhendrong Chen from Wuhan University. Here's the content of our slide. Let's begin with the motivation behind our work. The rapid development of multimedia technology has led to a significant increase in demand for video transmission and storage. Often, video platforms have limitations on high frame rates and resolutions, necessitating video resampling. The core task of video space-time resampling is to jointly optimize both temporal and spatial downsampling and upsampling processes. This joint optimization aims to achieve superior spatio-temporal reconstruction results compared to handling these processes separately. However, video resampling faces two major challenges. Firstly, the effective modeling of temporal resampling. Most existing methods focus heavily on spatial resampling, often neglecting the complexities of the temporal domain. While video frame interpolation (VFI) techniques have advanced, accurately reconstructing extreme or complex motion remains a significant hurdle. Secondly, achieving continuous space-time resampling is an underexplored area. Current models are typically limited to fixed, often integer-based, temporal and spatial resampling factors and cannot handle fractional frame rate transformations, such as converting 24 fps video to 30 fps. Traditional, frame-skipping and VI approaches often struggle to preserve motion information lost from high frame rate videos, leading to artifacts like significant blurring, as you can see in the example. To address this, we propose an invertible motion steganography module, termed IMSM. The IMSM is designed to embed motion information from high frame rate videos into the downsampled, lower frame rate frames in a visually imperceptible manner. Crucially, its reversible nature allows this hidden motion information to be recovered, which aids in reconstructing high frame rate videos with high fidelity. This leads us to the main contributions of our work. Our contributions can be summarized as follows. First, to tackle the issue of irrecoverable motion information lost during temporal downsampling, we introduce the Invertible Motion Steganography module, IMSM. This module imperceptibly embeds motion information from high frame rate videos into low frame rate frames. Its reversibility is key, allowing for the restoration of this motion information, thereby facilitating high-quality spatiotemporal reconstruction. Second, to the best of our knowledge, this is the first work to achieve continuous spatiotemporal resampling. We propose a straightforward yet effective 3D implicit modulation module, along with a corresponding training strategy. This enables continuous spatiotemporal modulation, importantly including non-integer frame rate conversions like 30 fps to 24 fps and vice versa. Finally, extensive experiments demonstrate that our proposed method excels in various video restoration tasks, including temporal resampling, spatial resampling, and combined spatiotemporal resampling, showcasing its flexibility and high performance. Now, let's delve into the methodology of our approach. This slide shows the overall architecture and data flow of our proposed method. The downsampling process, indicated by the red arrows, begins with input high-resolution HA frames. These are first processed by a downsample backbone and a downsampler to obtain latent features. These features, which often exhibit motion ghosting, are then passed through our Invertible Motion Steganography module, IMSM, in the forward direction to generate low-resolution LA images with embedded motion. For the upsampling process, shown by purple arrows, the LA images are first fed into the IMSM in its backward direction to recover the latent features. Then, an upsample backbone and an upsampler are used to enhance and upsample these features, restoring the super-resolved senior output. Let's look closer at the Invertible Motion Steganography module. Its core idea is to manage motion information effectively. We train our system in two stages. In the first stage, a downsampler and upsampler are trained together. The downsampler learns to produce latent features that are rich in information for reconstruction, but these features might exhibit motion ghosting artifacts. This is where IMSM comes in during the second stage. The forward process of IMSM takes these motion-ghosted latent features and transforms them into standard, visually pleasing low frame rate RGB images, but with the crucial motion information now imperceptibly embedded. Then, for upsampling, the backward process of IMSM can take these RGB images and perfectly reverse the transformation, recovering the latent features needed by the upsampler. The architecture of the IMSM is composed of several invertible cells that utilize enhanced affine transformations. Here, and represent learnable functions, typically implemented as neural networks like our dense 3D blocks, to extract spatiotemporal features. This structure ensures that the motion information embedded during the forward pass can be accurately recovered during the backward pass. For continuous resampling, we introduce a 3D implicit modulation technique. This extends the concept of 2D local implicit functions, which represent images continuously, into the 3D spatiotemporal domain. This allows our model to define and query feature values at any continuous coordinate in space and time. The feature at a specific point is calculated by looking at its 8 nearest neighbors in the spatiotemporal grid, combining them with learned weights, and then passing this through a small MLP. Our resampling backbone consists of a downscale and an upscale path. The downscale backbone, shown on the left, uses multiple 3D residual blocks. Each block is a Conv3D prelude Conv3D structure designed to efficiently extract spatiotemporal features. The upscale backbone, on the right, employs 2 types of modules. When both spatial and temporal resolutions are altered, we use 3D Swin Transformer Layers (STL). For temporal-only resampling, we use dense 3D blocks D3B made of depth-wise separable convolutions to reduce memory for high-resolution inputs. These modules are stacked to form the upsampling network. Next, we will discuss the experimental results for our experiments. We trained and tested different methods on several commonly adopted datasets. Our training is a 2-stage process. In stage 1, we train the resampling model end-to-end using Charbonnier loss, supervising only the final upsampler output, allowing the latent features to capture rich motion information. In stage 2, we train the IMSM to transform these motion-blurred latent features into visually pleasing RGB images, while also ensuring it can reverse this process. We use an invertible loss that supervises both forward and backward transformations, accounting for quantization. For testing, we evaluated fixed spatiotemporal resampling, specifically 2 times temporal time 2 times space 1 times and 2 times temporal with 4 times spatial time 2 times space 4 times. We also tested continuous resampling by fixing temporal scaling at 2 times and varying spatial scales with non-integer values like s is equal to 2.4, 2.8, and so on. This table presents the quantitative comparisons for fixed space-time resampling tasks. For the time 2 times space 1 times scenario, our method significantly outperforms state-of-the-art video frame interpolation methods and the joint resampling method STAA on both Vimeo 90K and Vid4 datasets in both RGB and Y-space metrics. For instance, on Vimeo 90K Y-space, our method achieves notable improvement over others. Similarly, for the time 2 times space 4 TIMS task, our approach surpasses sequential VFI and video super resolution combinations, as well as one-stage space-time video super resolution methods and STAA. We achieve a PSNA of 40.57 on Vimeo 90K Y-space, again demonstrating a clear advantage here. We show results for continuous space-time resampling on the SPMCS dataset. With a temporal factor of 2 times and various non-integer spatial scaling factors S. As you can see, our method consistently outperforms other methods like Videoinger, Motif, and MSMA across all tested spatial scales. from S is equal to 2.0 to S is equal to 4.0 in both RGB and Y space. For example, at S is equal to 2.4, our method achieves 37.59 psna in Y space, while the next best is 34.33. This highlights the effectiveness of our 3D implicit modulation for flexible spatial scaling. This slide shows visual qualitative comparisons for the time 2 times space 1 times case on the vid4 dataset, compared to methods like FLAVR, MAV, and Former, which tend to produce noticeable blurring artifacts, especially in regions with significant nonlinear motion. Our method reconstructs sharper details and preserves motion more faithfully, resulting in outputs that are visually closer to the ground truth. Under other space-time resampling factors, our method also shows significant advantages. Finally, let's summarize the conclusions of our work. In this paper, we addressed two critical challenges in video resampling. Firstly, to preserve motion information effectively during temporal downsampling, we developed the Invertible Motion Steganography module (IMSM). This module successfully embeds motion data from high frame rate videos into downsampled frames in a visually imperceptible way, and its reversibility allows for high-quality reconstruction. Secondly, to achieve flexible spatiotemporal resampling, we proposed a 3D implicit modulation technique. This allows for continuous spatiotemporal resampling, importantly including non-integer frame rate conversions, a capability largely missing in prior works. Our comprehensive experiments have demonstrated the effectiveness of these contributions, showing that our method significantly outperforms existing solutions across various video resampling tasks with high flexibility and performance. Thank you for your attention.